Good morning. My name is James Gilchrist, and I'm from the Department of Chemical and Biomolecular Engineering at Lehigh University. I want to thank you very much for attending this talk. And I'm really upset that we can't all be in one place because it's really the networking of this meeting that makes it so special. I've been involved with ISCST for approximately 10 years, and each year very much enjoyed all the interactions and the wonderful science. At least we're seeing the science now, but it is more difficult to connect. If anyone wishes to get in touch with me about the details of my work after this meeting, please reach out to gilchrist@lehigh.edu. So just to give you a little bit of background, our expertise really is in particle science. Whether you're thinking about synthesizing particles, which we do emulsion polymers and oxide particles, all the way up to how they will aggregate, crystallize, or have field-driven assembly under different conditions. And when I say field, in this situation, I'm thinking mostly flow fields. And of course, all the way up to processing conditions, where you have to think about the constitutive properties of these things, like the rheology and transport and solid handling and scale up. And so while the particles in the processes might scale from nanoscale all the way up to meters, the assembly methods usually are happening down at the colloidal scale or maybe in the blue region where capillary interactions matter. And so for many years now, we've been studying nanostructured coatings. We have now a roll-to-roll process in which we make monolayers of particles, and we can do layer by layer assembly of monolayers to make 3D crystals. We do a lot of Janus particle fabrication, in fact, where we can make a layer of particles, then coat a metal on it, and then make magnetic or other functionalized materials. And we've been, again, working in this area maybe for 15 years. I didn't put all our citations here, but maybe 30 publications and a number of patents, applications ranging from LEDs, OLEDs, coatings for solar cells, dye-sensitized solar cells, and then a lot of biomems work with collaborators as well. We also make polymeric membranes this way, and we've even gotten to the point where we've used other particles like cellulose particles that both modify the rheology and the microstructure at the same time. The talk I'm going to talk about today is enabled by an NSF grant, and the citation to the work that I'm going to mostly highlight today is shown there in the bottom in scientific reports this year. And so the drive for coatings is easy enough to rationalize with this crowd, whether you're talking about particle-based coatings such as latex paints, auto paints, which we work a lot with collaborators like PPG. We talked a little bit yesterday about that, and I'll talk some more about that today. Paints that go into inkjet printing, even cosmetics where the substrate is your skin. But I'm really today motivated by pharmaceutical-based coatings, and you can think of like tableting or the coatings that you go on tablets, but more of the films that are the edible type, where you make a film and then you eat it and it'll dissolve, or you put it against your skin or underneath your tongue and it'll deliver a certain amount of drug. And the challenges here are particularly different. For the FDA, this has to be easy and reproducible, and the rheology has to be well known. And of course, the processing conditions to get this exact same product all the time is critical to have this is really a functional material with a given drug delivery rate. And drug uniformity throughout the film is key. So when we think of particles migrating and assembling, sometimes that is to your advantage or disadvantage during processing conditions for these applications. And so for those of you who are a little newer to the coating world, I mean, coating is extremely important. But I like to use this analogy that if you like to play golf or watch golf on TV, the pros, they drive for show and they putt for dough, meaning when they drive, they whack the ball and it goes 300 yards and everyone cheers, and that's amazing. But really, they don't make a dime until they put the ball in the hole. And so my analogy for coatings is like golf. Instead of drive for show, putt for dough, I'm thinking coat for show, dry for dough. Now we know if the coating doesn't work at all, there's nothing to dry. But also, the coating can work perfectly, and the drying process itself will lock in the microstructure and the features that you need. And you're trying to control how that entered the drying process by controlling the coating process. So today, it's really less of a discussion about coatings and more a discussion about drying of particulate-based films. And so there are really legends in this area, certainly the Scriven group and all the other groups like the Kumar group and the Francis group at Minnesota, and then many broad at, I can't list all the institutions, but I have a great deal of respect for all the roll-to-roll processing that occurs, you know, and has been displayed at this conference already. And so, you know, if I'm just taking citations that include pharmaceutical processing directly, it's the same equations that everyone is using. And of course, we all know the challenges of actually using laboratory equipment and trying to control those conditions and then scale it up. Well, right now we're going to think about scaling down to the microscopic microstructure. And so, for instance, you could look at the particle assembly in these systems by looking at scattering. So if you send, you know, something to scatter through these films, I believe this is X-ray scattering, you can see maybe at different times in the film whether the particles were well distributed or they're aggregated and how that changes. And here, pH was used to change the relative attractions between particles. And so our study today is actually closest to this. This might be not quite as familiar to the coating world, but certainly there's a lot of people in this field that have combined colloids and coatings and then looked very closely at how the microstructure evolves. And so whether you're just using confocal microscopy to get average density and scan, and then of course here where they're showing AFM of the top surface, or even looking at changing particle size to dynamically change the particle size ratio to look at partitioning or segregation in these systems. Now, most studies that are experimental actually do what's up on the right-hand side, which, you know, we've seen already many examples of where you section, you use like cryo SEM or SEM to section your film, and then look where the particles inside went. But of course, the challenge there is you can't see while it's happening. And one of the ways to do this is to perform simulations where there have been great simulations, for instance, in the Ketty group and others like the Pangianopoulos group at Princeton, where they've looked at particle and different, you know, binary systems and particle-polymer systems to understand the size ratio and how that caused partitioning in these systems. And so we all know that's driven by a Peckley number. For most of the things we're going to talk about today, the Peckley number is high because the viscosity is relatively high and the diffusivity is relatively low. And so I'm not going to get too worked up about that because we also are going to have particles that have attractive interactions. And so our goal today is to investigate and understand microstructure dynamics during processing of these films. And it's going to be, if you think about it's concentrating, but it's also changing in microstructure. And I think that's a lot of the things, that's one of the challenges that we're missing in today's simulations, this kind of atomistic view of things. And so the setup is really simple. We're not going to look at roll-to-roll coatings, but we could certainly, if I was handed a sample of a roll-to-roll coating, you know, hot off the press, or just as it was coated, and then put it on the microscope, and then perform a drying operation that's similar to that in industry. We certainly can do that. Right now, all I'm going to do is just blade coat suspension, and this material is, well, it's going to be covered so that the drying is mostly unidirectional, which is more similar to what happens in you know, roll-to-roll processing conditions. And then we're going to scan through the system, and I'll talk about that in a second. The constituents are similar to what they use in the pharmaceutical industry. They use an edible PEO, which has a relatively high molecular weight, which you can change the control viscosity for coating, but most of the time you're thinking about drug delivery rate and dissolution. And so we've just picked an off-the-shelf commercially available polymer. It has a polydispersity certainly to that molecular weight. And we're going to be at 5% by weight PEO or 10% by weight PEO. And then we're going to, all those concentrations are well above the overlap concentration right from the bat. And then we're going to also add roughly micron scale silica particles that are fluorescent. So that allows us to image. And then we're going to change the pH to change the interactions between those silica particles. And so the drying process now, again, that's just blade coating first, and then we're going to let it dry for, all these samples dry in roughly an hour, but we're going to just rescale that time. And then we're going to use laser scanning confocal microscopy to scan through the system. And that what allows us to do is sectioning, optical sectioning at different levels. Or what we can do is just scan at a certain height and do microbiology. So today I'll talk less about microbiology, but at the talk we had yesterday, and if you have questions about this, I just wanted to highlight, even when you have a very complex flow, as long as you can see particles on the inside while you're flowing, what you can do is determine the local velocity, of course, from PIV, but then you can zoom in even more to individual particle trajectories and back out this complicated motion and get the Brownian motion just to give you the ability to do microreology. And so for these kinds of samples, we can look at not only time and space at the same time of drying films. And this is very challenging to do because a lot of systems are non-opaque, and of course they have drying patterns that are very complicated, as shown on the left. That's a separate grant that we have in collaboration with PVG and great collaborators, especially Chris Worth and his students at Case Western. And so back to the main objective, we're just going to scan through these samples. And so mostly I'll show you 3D scans of these systems. And so just to talk a little bit about the rheology and changing pH and how that has an effect on the system, what we're going to do now is just put polymer and water. These are all the open symbols. And as I increase pH, what happens is you have a decrease in the rheology, and that's because it becomes a theta solvent or a poor solvent for the polymer, and it balls up on itself and lowers the viscosity. Now, as you can see, we also have shear thinning until we get out to roughly between 1 and 10 inverse seconds. But if we add silica, the blue lines shown here are these closed symbols where essentially we just have a small modification of the viscosity by adding 5% of these microspheres. But as we change the pH, now the viscosity increases. And essentially, the picture you can think of is at moderate pH, pH 7.5, everything is repulsive and things can flow around freely. But then at 2.5, you essentially neutralize the surface of your silica, and then you have heteroaggregation of polymer to surface into other particles. And so this is what sets up this network that causes shear thinning, but more importantly, perhaps, is a yield stress that gets set up that after about a pH of maybe 4 and lower, you start seeing a dramatically high, onset of yield stress. We can see this when we coat it. We can see this when we manipulate the fluids, but it's still certainly a relatively low yield stress. So you can think of still being able to coat these relatively freely. And so you can think every time I say pH 7.5 or neutral conditions, you can think of particles floating freely and really, not interacting with each other strongly. And then at 2.5, you'll have aggregation. And so the technique we're going to use today is 3D confocal microscopy. And the image or the movie I'm showing here is just a series of images as we scan through this. And what's great is we can scan very quickly. We scan usually, this image would scan about 25 by 17 micron volume, where each pixel is 100 nanometers. And we can do that every second. And we typically do that every 30 seconds through an hour of drying. And the goal here is to have simulation level detail of these experiments. So you can really watch as things dry. And as I'm showing in this movie, there is a complex evolution in these systems. And so a lot of the things that I'm going to show they look like simulations, but they're actually tracked particles from experiments. We did no simulations in this for this research. And just to start, I'm going to give you like a time evolution profile of the drying process. And so you can think initially this as the height from the substrate, and then the time during drying, where time equals 1, essentially the microstructure is arrested. Now there is a little bit of water, residual water, that's still diffusing through the polymer and colloid matrix, but essentially we don't expect to have any more microstructural rearrangements at this point. And what you can see is at the beginning, this is for pH 7.5, we have a relatively uniform system. And then as we go in time, you can see there's a little bit of sedimentation and a little bit of structure near the bottom surface because those colloids start to order and crystallize. You can see there's no drastic fluctuations in concentration. The colors now are 0 to 30%, if that's hard for you to read. And the blue area is simply where we cannot properly index match the particles with enough confidence that we can locate them. And the index matching changes in time. So if you start with a certain system and it's drying, you're losing solvent, the polymer is becoming more concentrated, the particles are becoming more concentrated. And as you go, actually the index matching gets worse and then much better as the polymer gets really concentrated between all the particles. And so we have this ability to kind of take average scans and get our concentrations. So if we look now on the left-hand side, this is pH 7.5. On the right-hand side, it's pH 2.5. And you can see now the ones on the left look very similar. In fact, in even the upper left one, you can see that interface come down. And there is some pushing of particles that are partitioning at the surface. And that's mainly because the Peckley number is greater than 1. And then we just simply didn't see that surface come all the way down just because the volume fractions and the thickness of the film was higher than what we're presenting here. In contrast, at pH 2.5, we see very drastic fluctuations in concentration. And you can think of this as how does the concentration go up and down, up and down? And really what's happening is there is a gel that has a microstructure and you're sampling different points of that microstructure at different times. And if I showed you 20 experiments, all of them look different in this initial time. And then eventually what happens is that you see that things become more uniform again and very concentrated. And again, at a higher weight percent of PEO, you have initial fluctuations, and then eventually you'll see a concentration of the film. And so just to give you some of the dynamics that occur here, the pH 7.5, the video of this is located on the left. And the only reason why it looks like a shorter film at first is because we can't scan as deep. But then eventually you can see the top surface come into view. And what you see, first particles are moving what looks like randomly. And they're actually flowing very quickly in this frame, except for the particles near the bottom. And then later, as the viscosity goes way up, the particle of viscosity goes, the suspension viscosity gets so high that these particles now you can see the flow velocities and track them and look at the final microstructure. In contrast, on the right, you can see something that looks like a very heteroaggregated gel and very open structure that's changing very dynamically in time. It looks like a tempest in a teapot is what we call it. And so as you can see this grow and then settle, the microstructure starts to look similar, but we'll show you some very subtle differences that you get because of the nano precision of finding these particles in our experiments. And so because we can do this with such precision, we can use the same tools that people who work with numerics and simulations use in theirs. So for instance, we're just going to look at a GFR, or what is the radial distance of particles, and looking at the density over the distance from a single particle and averaging that. And so for a crystal, you'd see lots of peaks. And for a disordered system, you'd see it's relatively flat. And in this case, for these systems where it's random or gels, it doesn't actually tell you a lot of information. What we see is the first peak in 7.5 is actually relatively flat, and that first peak develops. Now, what may happen over time is that we have depletion interactions because we get so concentrated in polymer. And so to say that this is perfectly a liquid and perfectly a gel, it's hard to say that, but we're going to have some evidence that I'm going to show you later on that makes you think that this is really more like a fluid where the concentration every time, you can think of that as if I were to mix it at those concentrations and then randomize where everything is, what does that profile look like? And so on the right-hand side, it's harder to track these particles because number one, there's less in view. And number two, it's a disordered system. GFR just simply isn't the best way to sample this. But you can see at later times, GFR looks about the same. So that doesn't tell us much in this case. And essentially GFR is the same thing as you get from scattering. So in this subtle microstructure changes, you really can't back out the microstructure by scanning with some sort of scattering device as well as you could in this case. So let me show you some of the other data we can get. So we can look at the number of neighbors in contact. So we can look at 2R out, or roughly 2R, with a little bit of tolerance, and find how many particles are essentially touching this particle. And then we'll talk a little bit about Voronoi polyhedra, but it's essentially a similar analysis about figuring out number of nearest neighbors, but non-touching. And so for number of neighbors in contact, we've done this kind of spread plot where initially the average is between 0 and 1, and you can see very few particles have 2 neighbors initially. And then as it gets very dense, they're compacted close to each other, and then you get a very large broadening of this as things dry. And you can see at the end, your neighbors in contact, and this is in 3D, are probably somewhere between 3 and 6, or maybe even 7. And you can see that's lower, in fact, for neighbors of contact for higher concentrations of polymer because the particles just can't approach each other as well because there's some polymer left in the interstices between those particles. In contrast, when you have particles that are attractive on the onset, we're going to see wild fluctuations, but you can see the average still, you know, like it's a strong gel, which has on average 3 nearest neighbors and forms a fully connected network. Now, as things dry, what happens is, we said the concentration goes up, and mainly this is a compression of this film, and it's breaking the gel, okay? So you can think of this as a very chemically driven process, and everything at 2.5 is very mechanically driven process. Now, for many people who, you know, look at rheology and coatings, maybe that's not too surprising. But again, thinking back to being able to measure this specifically and the structure is kind of new in this field. And so what we can do with the Voronoi polyhedra is essentially what you do is draw a line between the center of each particle, and at the mid plane of that line, draw up this plane, and then you can reproduce this for all particles neighboring. And in this case, we're just doing it in 2D, but you can imagine in 3D, if it's a perfect crystal, it'd have 12 nearest neighbors, and it'd have a polygon that's characteristic of like an FCC crystal. Now, of course, we are looking at disordered systems, so the dotted line is that minimum volume that I just described. And now we're going to always look at distributions of volumes that are much larger. And you can see many of these are it's as much as, you know, 10, 15, 20 times as large as like the standard one. And so what I'm showing you on the left-hand side now is a probability distribution of all the different types of these free volume spaces taken up by particles. And you can see it starts relatively broad, and then as it dries, gets narrower and narrower, and eventually compacts down to the point where essentially there's no change in microstructure anymore. And so that was for pH 7.5. At pH 2.5, we see something very different. And what's different is initially, in fact, the gel structure is more compact, the microstructure in general. That's because you have particles that are touching, and then particles that are very far away from each other, and very open voids that are sliced up into these weird pie shapes, if you know much about Voronoi polyhedra. But what you can see is all of these, even though it's flowing and changing and evolving, all of these distributions are the same until eventually they break and snap into a new configuration. And this is what I meant by a gradual chemical process versus a sudden drastic mechanical process. So what we have here is bits of gel flowing around, and eventually you have enough capillary pressure to pull down and break those primary chunks. And so just comparing to that movie, we have color-coded images of that video now, and comparing to the different distributions. So this red one goes with this wider distribution, this purple one goes with the end of time drying situation. And this is just like the video I showed you before. You can see, it just looks denser essentially as you go through. Whereas on the right-hand side, the microstructure is changing drastically, but it turns out the micro scale microstructure isn't changing, it is breaking up in chunks and flowing, right? And then eventually the capillary forces. But if we had more polymer in here, we could arrest that microstructure in here. So really, it really depends on what density of particles and what you really need to have as a binder for your final, for instance, dissolution. I forgot to say something very important early on, is that if you think of this as a drug delivery system, of course, silica would be a horrible drug to take. But in this case, it's a surrogate for that drug, okay? And you can change the surface properties of that silica, fine-tuned with the idea that you can pick any drug off the shelf and probably change the chemistry of the silica to behave like that drug. And then you can have polydispersity of those particles as desired as well. So how does this relate to pharmaceutical processes? It actually can relate quite a bit. So just to finish off the data here, at 10 weight percent, you can see that we don't have as drastic of changes, and we end up with a much more open microstructure. Now, something we discovered that was a little bit unique to these systems, and I haven't found really in the analysis, there are many other papers that analyze microstructure this way, but it looks like there's a self-similar thing happening here. And what it is, there's some articles long ago talking about how they should have a log normal distribution. And that's why we plot a log linear profile, because you can, number one, see these tails better way out to the distribution. Then you can see the difference in those tails. Now, I also have to remind you that we have something between a few thousand and 10,000 particles in each scan, and then we average over many scans, right? And so just to think about this probability, down below about 10 to the third, all this noise back here and down here at this end of the tail, essentially what that's telling you is it is truly noise. We don't have statistical representation. What we can do is fit these curves for everything above about, I think it was something like 2 or 5 times 10 to the minus 3, and just fit the rounded tops of those. And when we do that, we find something very interesting. So we can fit it to this log normal function. So it looks a lot like a Gaussian distribution with a log normal distribution of the Voronoi polyhedra. So mu is the mean, and this is the standard deviation of that fit. And so we use a 2-parameter fit. And in this case, the mean, what you can see, so the open symbols are those with pH 7.5, and the closed symbols are those at 2.5. The open symbols are always monotonically decreasing in the experiment. And the closed symbols, where it's a gel, sometimes go up and down and fluctuate quite a bit. But what's really telling is the standard deviation. And in fact, the standard deviation that was a very surprise discovery we've had was that for, again, the chemical-like drawing process where you would essentially think of these particles as just floating around, they might be gelling eventually in the process, but we saw no evidence of that from the Voronoi polyhedra distributions. And you have this standard deviation that is flat for all drying conditions from the very beginning to the very end. That standard deviation has a very little standard deviation of the standard deviation, right? Now for the samples that were gel, that's completely different. The fitting for each one of those times is completely different. And again, you could average over many samples and you see that it simply is not monotonic. It will change. The structure is very complicated. It has this history of drying essentially. But at the very end, it starts coming down within range of what you'd find in that chemical-like drying process where the particles are not attractive. And so this is a clear signature of, if you're scanning through your sample, number one, at what point is it really done drying? Well, obviously just watching scattering and motion of particles will tell you something about that. But it also could tell you a lot about do you have a uniform effective distribution of things where if you could freeze and lock in that microstructure, you can do that very similarly in this condition, but you have more variability and yet more sample space to find microstructure that you could freeze in as well. Now doing this reproducibly is a challenge. So with that, I just want to give you a quick summary where at pH 7.5, we believe the particles are not attractive. They have a very weak interaction. What we see is, stabilization of that film and flow, and then eventually we may see aggregation through depletion, but there's no evidence of that in the plots I just showed you, and eventually make this very dense polymer colloid film. And then at the end, and in contrast, we can have a heteroaggregated system where the particles are attracted to each other through these essentially heteroaggregated polymer branches. And now you can see that you essentially start with a very open gel that changes its microstructure drastically and then leaves you with a structure that may or may not have similar properties. So my time is about up. I certainly want to say that I think everyone in this conference would agree that it's not as boring as watching the paint dry. I think coding process is amazing, drying processes are amazing, and really it's these 3D structured coatings I think are really the challenge. I believe I visited 3M several years ago, and that's what they said was the novelty is, can you make 3D structured coatings? So this is a lot of 3D disordered but structured coatings, and of course a lot of my other research really focused on well-ordered coatings. And we have discovered some new fundamental insights of this structural evolution and something that you could compare directly to simulation, which is ideal for maybe even benchmarking simulations that would include microstructure in these samples. So with that, I first want to thank my student who's just been an outstanding student. She's supported by the Royal Thai Scholarship. And then we also have an eager grant from NSF that has funded this. And I'm going to talk a little bit about instabilities, other drying instabilities later on this morning. And I'd love for you to come to that talk because that's a real wild ride, but a very cool pattern formation topic. And with that, I'd be happy to answer any questions. Thank you.